right? And that's under ionic. How about the other ones? Are they electrolytes? All right, so this is an electrolyte in aqueous solution, okay? So an aqueous solution. So we know that electrolytes conduct electricity in aqueous state. What about metallic things? Do they conduct electricity? Yes, but what state? In their solid state, right? So we know that they are conductors, but we just remember that they're in their solid state when they're conductors, whereas ionic compounds are not conductive in their solid state, but they are conductive in their aqueous state. Okay, give me a property of covalent. On this side of the room. Anybody over there? Killing me, people. Covalent. Give me a covalent property. Low melting point. Great. Okay, so like butter. All right. Low melting point. All right, give me another property of ionic. Hannah.
It's a metal and a non-metal.
Okay, so metal and non-metal together. And I'll go ahead and add non-metal, non-metal together. I want to hear more properties versus like what they're composed of. All right, yeah, go for it, Sarah.
Ionic is metallic is malleable.
Metallic are malleable. Good. Malleable and ductile. I'll go ahead and just add that one there since we're probably all thinking it. Yeah?
Product also really strong.
Really, really strong, right? So high melting point and strong bonds. All right? And then covalent, we understand that they have a low melting point. So what do you think the state of matter they normally exist in would be? Gases. And what were you going to say? No. Never. These things don't have charges. Good point, though. So ionic things have charges, right? A plus and a negative charge get together because they're electrostatically attracted. These have no charges. They are simply two things that share electrons. They don't give each other electrons, they share it. That's why they don't have a charge. And then what did I just say for ionic? No, gas. We said gases. Okay. So normally they're also very volatile. What does volatile mean again? They do what? They could explode, but that's not exactly the definition of volatile. So maybe their liquid state isn't stable, so then what do they change to? Gases. So like that deodorant you got on, does it make you smell good? Thank the Lord. All right. So it is volatile. If your body heat is warming it up, and it's kind of sending off little scents to other people, like, ooh, she smells real good today. And then otherwise, you know, it's just volatile, meaning it vaporizes easily. Okay, so that's a lot of stuff to know about ionic and covalent things in solutions. So, you know, chapter 16 is a lot about solutions. Jot down extra things that are not on your reading guide. We're just going to finish up chapter 16 things quickly, and then we'll move on and do some calculations today. So, looking at these three compounds, I want you to classify it as ionic, covalent, or metallic. And then we'll talk about which properties fit which one. So, write down the formulas first on your paper. Formulas. That means you are a boss at nomenclature. Write down the formulas. Oh, okay. Okay, sucrose sounds like glucose. Can you write down glucose and then I'll tell you what sucrose is? Write down glucose for sucrose right now. We are struggling on that back carpet. Ooh. Oh, okay. All right, let's start from the bottom because that's the easiest. Jacob, formula. Ready? This one. NaCl, because in your head you're like, sodium's got a what charge? 1, because it's in group. And it has 1 valence electron, so it loses that 1 valence electron. And chlorine is in group, so it has how many valences? 7. So then what happens to it? It gains 1 electron to get octet. You see, we're doing a review right now, yes? And some of you are like, I don't know. Okay, don't mumble. Say it out loud, but then if you're wrong, just fix your mistake. Okay, so sodium chloride, good. Sucrose, let's just go with glucose since you guys know that one. Okay, so this one you know it's ionic. Yes, how?
Metal, non-metal.
Right, metal, non-metal. This one you know is, how do you know?
They're all non-metal.
All non-metals. Carbon, hydrogen, oxygen are all on the right-hand upper corner, so they're all covalent. All non-metals would be covalent. This one's ionic. And this, oh yeah, you are so right. Hydrogen is in this weird place, but it is on the upper left-hand side. Sodium, okay, well, I know we can get that part. Yeah, go for it.
NaHCO2.
Beautiful. Okay, so bicarbonate, that bi is not di. Right? Remember, di means two. I saw a bunch of us trying to like add a two in there someplace. No. Di is two. Bi means to add a hydrogen. There's a hydrogen here with the carbonate, which is CO3 2 minus. So H plus and CO3 2 minus come together to make this happy bicarbonate species because the H, CO3 come together, and then the plus 1 and the negative 2 cancel out 1. So it's a negative 1 charge. That's why there's an imaginary 1 there. Whew. Okay. Ionic or covalent, though? Because you wrote ions, right? Sodium ion, carbonate ion, or bicarbonate ion, so it's ionic. Okay, so one, I'm going to label these 1, 2, and 3. What numbers will be conductive in solution? Say it again. 1 and 3, because what is conductive in solution? What kind of compounds? Ionic. So whichever ones you said were ionic were number 1 and 3. Which would dissolve in solution?
Oh wait, all.
Say again? All of them actually do quote unquote dissolve. So the word dissolve we use in everyday life is not really well defined. So most of the time whenever we talk about things going into solution, we're saying they ionize in solution. Remember the attack of the water molecules? Yeah, they're like ripping the ionic side apart. That to me means in chemistry terms dissociate or ionize. But a lot of times we use the word dissolve to mean that or to say that. The word dissolve is really generic. It just means, hey, water molecules surround you and you go into solution and we can't see you anymore. So, does sugar do that? Have you ever had like sweet tea? You're in the South, yes? Okay, do you see clumps of sugar in your tea or do you see it dissolve? Okay, well you see it dissolved, right? You know it's there because it's sweet and it's dissolved, so it's apparently dissolved. So the word dissolve is a big fat lie. We don't use it correct ever. The word dissociate would mean to be pulled apart. The word dissolve means to be hydrated by water. Okay, so that helps me with this one. Which one definitely ionize in water? Which ones? And? Right, guess what, guys? Ionize refer to the ionic ones. So that's number 1 and 3. This was all. Okay, but what would definitely not dissolve in water? We know some covalent compounds definitely do not dissolve in water. What's a good example?
Gold.
Covalent compounds. Thank you. Oil. Big, humongous carbon hydrogen chains do not mix well with water, therefore they don't dissolve in water. The one that dissolves in water, sucrose, is just a small sugar molecule. So it's cool to dissolve. Okay, yeah.
What is the difference between glucose and
Sucrose is a disaccharide. It's fructose and disaccharide. So glucose is a monosaccharide. It's a single ring, like this kind of thing. It's written, so this would be a disaccharide, and sucrose is C11H22O12, something like that. So it's just a little bit bigger. It's a fructose molecule and a glucose molecule together called sucrose. Okay, let's finish up chapter 15 stuff just really quickly from yesterday. But I believe, with my board working, it wasn't working yesterday at all. Actually, I lied, you were on 16. This is what you wrote down, I think from number 1 on the reading guide 16. What factors affect dissolving or solution processes? Tell me some things that affect the rate of dissolving or if something is going to dissolve. Hayden. Say it again. Agitation. So you can either put something in water and stare at it forever, or you can do what to it to make it dissolve faster? Stir it up. Right. You use a stirring rod in chemistry, or you can just stir it with something else at home. Yeah.
The surface area to dissolve the particles.
Right. So do you want a high surface area or a low surface area to increase the rate of dissolving?
High.
High surface area, but what size are the particles? Big particles or small particles?
Small.
Small particles. So the way that works, and this is one of the harder ones to really think about, but you can have a big block of sugar, and let's say each of the sides length comes with some type was 1 centimeter. Okay, 1 centimeter, 1 centimeter, and 1 centimeter. What would be the surface area of that? That's the volume. You said 1 centimeter cubed. That's the volume. Give me surface area. How many faces are on this cube? 6. What's the area of each face? 1 centimeter squared, right? So what's the total? 6 centimeters squared would be the total of all 6 faces together, right? But if I particulated that into many cubes, little bitty cubes, like dust particles, each of those faces on each individual tiny particle would sum to probably like 600. Total 600 centimeters cubed, just because you particulated it. So big surface area means really small particles. That will increase the collisions with everything else, and they'll react faster, they'll dissolve faster. More, agitation, surface area, temperature. Increasing temperature, we already know from our solubility curves, increases the rate of dissolving. Anything else? Pressure. Pressure is going to deal with gases mainly. So what from this do you not have? Nature of the salt. That's what our solute, that's what we said. And that just means like, hey, does it actually like each other? Does it mix? So that might be like polar and polar, like dissolves like, non-polar and non-polar, okay? Like dissolves like. And so that's just saying, are they compatible? Will polar things dissolve in polar things? Yeah. Will non-polar things dissolve in polar things?
No.
So that's just giving us a bit more information. But this is, a lot of this stuff is kind of common sense. So we know that these things that we denoted, they will affect if it will or how fast it will dissolve. So I'm saying it will change the rate of dissolving. That's what this means. It'll change the rate of dissolving. But you're not going to surpass the saturation point. So you can keep pouring sugar in that coffee or that sweet tea, but eventually is the sugar going to stop dissolving? Yeah, then you're going to have a big layer of sugar in the bottom. So when you take a swig, it's going to be like sugar pouring in your mouth because it doesn't dissolve. You know, eventually, like, that stops dissolving. So that's what I said. It doesn't change the amount. It only changes the rate of dissolving. Thumbs up and you're good here. That's what I said. You can actually take some notes in your reading guide because it's, like, pretty dang similar to what you guys already did. So, using your brains there. If you didn't do Chapter 16 reading guide, you don't know this as well. And that's okay. So, this is the part I want to go over here. Look at these pictures. What do you see? So, you know, the Battle of 1918, where the water particles crossed the barrier and attacked the salt. You guys didn't learn about this in history class? Not yet? Yeah? Water against sodium chloride? Okay. Tell whoever history, tell them what's right. Okay. So this right here is just called dynamic equilibrium. So it's another term that we need to be familiar with so that we can describe how solutions continue to dissolve. And they go back and forth, back and forth, back and forth. So dynamic means constantly changing. Changing is delta A. Kind of thing. And what do you think equilibrium refers to? Say it again. Equal. So even though it's still changing, the concentration of the solute that's dissolved is still equal to what it was previously. Yeah. Because delta means changing heat. So they sometimes refer to added heat. Delta also is a letter. And that's also a triangle. It's got many meanings. I don't know. I could make an equilateral triangle or a isosceles. I mean, I can go further, but you know, we'll stop now. Okay, so saturated solution means that whenever you have the salt in solution and the water is dissolving it, it's going to actually go back and forth between, so I'm going to put solute, solid, double-headed arrow to solute. What term would I mean? What I use here to indicate that it's dissolved in water? AQ, right? Aqueous. So this means sometimes the solid will actually attract back to, or the ion will attract back to its solid form, and it'll condense into solid, and then a water molecule will attack it and it'll pull it off and go to aqueous. It's going back and forth, back and forth, back and forth. That's why it's this double-headed arrow to show it's going back and forth, back and forth, back and forth. And that's what dynamic equilibrium refers to. And that's a term we'll use a lot. So that's what it says, solutes in dissolved in solution and then undissolved in solution. Okay. I think I have one more thing on chapter 16 right now. And that will be done from yesterday. Can I go forward? Thank you. Okay. Actually, oh yeah, this right here. Okay. So this is something we mentioned from a graphical standpoint yesterday, where we saw that gas is going down in concentration as the temperature went on. So I'm gonna turn the light back on, my people. It's sleepy on me. You gotta stand up. Go stand up. So reading the first part, what's new to you? Don't write down everything, okay? Write down what's new to you. What did we not learn or talk specifically about yesterday?
Oh,
We talked about increasing temperature and increasing the solubility of a solid. We talked about the fact that opposites is what's true for gases, that as temperature increases, they stay less dissolved, they bounce out of solution. And the reason why was that they have increased kinetic energy. And that was on your quiz, right? Yeah, okay, so that's something that's not really new. But if you want to put down an example, we've all experienced the flat soda, right? It was left out in the hot, the bubbles came out of it, now it's just sugary water, flavored water, whatever we're gonna call it. So that's just a good example if you would like to write that down. The new stuff's really below here, and that's more specifically what I'll talk about here. And I think we had one Mythbusters experiment that's related to pressure and gases. So here's the law that you guys wrote down on your reading guide, so if you want to add to that, that's fine. Henry's law states that when you change the pressure over the top of a liquid with gases dissolved in it, you're going to change the amount of gas that will be dissolved in it. What's a great example of that? Pressure on top of a liquid, gas bubbles inside the liquid. Say again? Well, the pressure has to be contained, so I don't have like a seal on top of my boiling water. Yeah. Yeah, soda pop, right? So if you have a 2-liter bottle and you open it, we've already talked about this. What happens to it? What's releasing? But the pressure that the gases caused that were hanging out on top of the soda bottle. So I'm going to scroll down a little bit here. Is that okay? I hope so. Okay. So let's draw. It's going to look like a spaceship. Yeah? 2-liter bottle. Okay, 2-liter bottle. Just specify what this is. Okay, there's the liquid. What's up here in the top? Gas, right? And I'll call it pressurized. Pressurized gas. Usually CO2, since they don't want to, or maybe some nitrogen. They don't put really too many crazy gases up there. And then we have bubbles in here. Okay, so if you're a drawer, here you go. And whenever you have the pressurized system on top and you have not opened the lid, then all these gas bubbles stay in. So increasing pressure causes an increase in solubility. S is solubility of a gas. Once I pop the top, what happens? Right, these bubbles, the gases that are up here, they come out. And then these bubbles start to come out too. Not out of the side of the container, like indicated here, but out of the top of the container. Yeah.
So would this go for the same thing as if there was no water or anything liquid in there?
Yeah, probably, but since we're talking about concentration or solubility, we have to refer to solvent and solute. That's why it's indicating specifically, Henry's law specifically in the liquid solution. So if I decrease the pressure on top, I decrease the solubility of the solute, and the solute is the gas. Gas right there. So that's all Henry's law is. So the equation is S1 over P1 is equal to S2 over P2, but that shows the direct relationship of it. Just like our gas laws, anything that was on top of each other was a direct relationship. And this is something I think you guys are very familiar with because we've all opened a bottle of soda before. So a lot of times the pressure will be given to you as like atmospheres, and the solubility might be given to you as like grams per liter. Let's talk about the solubility there, or it might be moles per liter. It depends on what the question states for us here. Give me a thumbs up when you're good here. Okay, and some of you guys read this already in your reading class, so you're like, ah, got it, didn't got it. So, oh, while you're finishing that, I have to get something for you in a second. I'll get it. Forgot to get my pen note. Oh, okay. All right, so take maybe not 10 minutes. You guys have the molarity worksheets in the front of your desk. Okay. Some people took some yesterday, so if you took one yesterday, just leave it here today. Pass back the molarity worksheets. And not the readings, not the articles, just the molarity worksheet. And go to Model 2. Yep, you started it yesterday. Go through number 9 on Model 2. Go through Model 9 on number 2. And I'm going to go grab some funds.
Sounds like me on
The polarity of the solution is calculated. Well, I have one exposed. Let's see if I can find it. Thanks. I gotta look at
Only through question 9, that's it. You may have reached question 9 yesterday, but I'll study out.
the polarity of the solution.
What number are we on, by the way? I'm just curious. Okay, if you're already past 9, then help somebody else out.
Back to there.
Are you a fairy?
I'm a fairy. Alright, raise your hand if you're on question 9 already.
No, they're right.
Okay, cool. Okay.
Okay, so I'm going on vacation, so I'm getting on a plane after school tomorrow. So I'm gonna miss Friday, Monday, and Tuesday. So I just want to know if there's like work I can bring with me here. Yeah.
I got it.
Okay.
I didn't hear you guys. Okay, while I'm standing here, I am a fairy. I'm a magical fairy. And I'm going to do a fairy trick for you. Okay, if you look at this, what does this look like to you? Water. Okay, you have to watch it closely, so I'm standing in the middle. Okay, all eyes on fairy magic. Alright, at the tip of my magic wand, touches this, it's going to be accurate. Feel it. Pass it around. Pass it around, hurry. You know what he does? He transfers. You're welcome. Take my fairy spell brush. Pass it around. Pass it around. Right. Yeah. Okay. You break my heart every day. Here. Here, like a little. Okay, what happened? You see it? Those of you on this side? My heart is stone. Oh, I actually have a warm heart now, right? Isn't it warm?
Yeah.
Yeah? Pass that around that 7. Oh, they're going to Jesus. Alright, so what do you know? What was in that solution? Or what kind of solution was that? Both of these. Super saturated. So what did I do to it? I disturbed it. What do you think I disturbed it with? I did it like this and nothing happened, right? I actually had something on the end of my fairy wand. It was powder that solution is made up of. It's sodium acetate. Okay, so I added one tiny more crystal, and it was like, oh, too much, can't handle this nonsense. Boom, desaturates. And so instead of having a saturated or supersaturated solution, it all precipitates out. Where is that, by the way? You can just out in the back last station, okay? Cool, right? I mean, it was warm. So, awesome. All right, so I'm gonna keep the fairy wings on. Since we've already made it through a lot of this, you guys can quickly tell me this so we can move on, okay? So, get ready. Phone away. Oh wait, because this is now distracting. Distracted me. I'm not distracting you. Away. Okay, so a glass filled with the concentrated lemonade solution from Model 1. Is the solution in the glass the same as the concentration as the solution in the pitcher? Yes or no? Okay, so this the lemonade that's poured in from the pitcher in the glass, do they taste the same, do you think? Yeah, so is the concentration of lemonade the same? Yes. Why does it matter that's in a smaller container? No, it's the same solution concentration, so it's the same solution concentration. If not, we'd have a really hard time refilling our glasses at a restaurant. Be like, okay, let me get it exactly right for you, right? Because then a waiter and waitress would never get it right. Okay, does the solution in yeah? So does the solution in the glass contain the same number of solute particles as the solution in the pitcher? No. Why? Right, it's a smaller number of particles in that container. Because the big one had a lot of particles, the little one has a couple of particles. But explain how this can be true if they have lesser particles. It's a ratio, right? So if I had 10 particles in the big container and 10 particles in 100 milliliters, then what would be my ratio in my glass? Any ratio will work.
1 to 10.
Huh?
1 to 10.
1 to 10. So what did you do to both of those?
You just divide it by 10.
Right, 1 particle per 10 milliliters, which would be maybe the size of a glass versus the pitcher thing. Yeah? Pitcher. Okay. And so it's just the same ratio. That's what molarity is. And molarity is a concentration unit. We've already heard about molarity before, but we're just going to go a bit more in depth now, okay? So between the two of these particles, 10 over 100 and 10 over 10, which is more concentrated? Say it again. They have the same concentration. Why? Because they have the same ratio. Okay, so we use the words dilute and concentration or concentrated to qualitatively describe something. What does qualitatively mean again? Qualitative, not numbers, right? It's more about like just a description. Like there's a lot in here, there's a little in here. Did you hear any numbers? No, but I could say something was 5 molar versus 2 molar, and that would give us numbers, and that would be a what kind of data point? Quantitative. Good. So that's really all that little warm up was about. And there's some more pictures here. Oh no, this one I didn't want to show you. So if I wanted, you probably read through, if I wanted to calculate the molarity of this solution, by the way, what is the name of the solution? Copper 2 chloride, right? Because it's a 2 charge, you have to say 2. How would you figure out the molarity of this solution? What's the ratio? 0.06 moles over. So you guys can do that in your head. What's the molarity? 1 molar, right? 1 m is 1 molar. Instead of saying molarity, you say molar. It's not totally different. It's just slightly different. And then this would be 0.18 moles over 0.06 liters. What's that? 3 molar, right? And you can see the numbers. They're right there. I know you can see them. But you'll notice that this one is, which would you say is diluted? The first one. This is the concentrated one. It's 3 molar. This is the diluted one because it's 1 molar. But the diluted nature, or the diluted and concentrated terms don't give us exact values. They give us relative values. So we're just going to be talking in those terms today. So this is what I just described. If you need to write down anything, do so now. If you understand, because it's common sense, we're good. We're going to talk about molarity now. Give me a second just to read it if you need to. But I think this part is pretty easy, actually. Chapter 16 ain't so bad. And this brings up a couple of people's mythbusters. If you've not fixed it yet, I don't get emails whenever you fix anything. Sometimes I do, sometimes I don't. Specifically, if you want me to, like, if you want to ask me a question, please ask it to me or email it to me, because I've approved most of y'all's procedures. If yours has not been approved, then please get with me, because it's probably because it wasn't detailed enough, or there wasn't quantitative and qualitative data that you're collecting, or I didn't know enough about what you're going to do. So make sure you get with me. Okay, let's talk about molarity now. Molarity. This is at least, I'll go back to just give me 1 second. That right there, that formula, is going to be your go-to. Write it big on your paper, okay? Write it real big, and then jot down anything from the top that you need. So this is a specific way of expressing concentration in a quantitative way, so a specific number. And you can see the verbal description, a number of moles of solute per liter of solution, or just you can see the mathematical expression, moles of solute per liters of solution. Don't forget that solution is both solute and solvent, right? So we have our terms from yesterday we have to employ. And then whenever you're talking about molarity, we always label it as capital M. You're familiar with that some because we've dealt with that with other problems before in stoichiometry. And then when you say something about it, like 2M sodium hydroxide, that's called 2 molar. That's how you phrase it, sodium hydroxide. And the last little blurb up here is that it's an intensive property. And that is one term we talked about in Unit 1, a long time ago. And so if you don't remember it, this is what it means. The molarity does not depend on the amount of substance you have. That's why you told me that liter of lemonade and the cup of lemonade were the same concentration. Didn't matter what volume of stuff I had, it was the ratio that mattered, the moles per liter, moles per volume that mattered. So the only thing is just make sure that we go to liters in our problems and we're good. So I'm going to do 3 problems and then we'll let you guys practice, and then we'll talk about molality. Molarity and molality. 2 different things. Okay, so whenever you are writing or doing a problem like this, I prefer for you to write down your knowns, solve for your, think about what your given is, and then a lot of times it's easy to get moles first, so that might be what you need to do, and then evaluate like, hey, does this make sense? And that's just kind of our general theme on how we solve all of our problems. So I'm going to start you here doing this process. So, what is the molar concentration? So what am I asked for right now? So when you say molar concentration, what do you mean by that? Molarity. And when you say molarity, what do you mean by that? Thank you. Moles of what solute in this? What is the solute in this case? NaCl, right? So NaCl. So question is moles of solute over, right, liters of solution. So that's really what our question is, right there. And so if you kind of think about your question at first, then plug in your givens, then you should be good. So what is the molar concentration, this, of a 5-liter solution containing 4.3 moles of sodium chloride? How do you set this up, guys? Say again, for me, Hayden. So 4.3 is our moles of solute. And over what? 5.00 liters of solution. It's set up exactly the way we set up our question. Plug it in. What you guys get? Calculators out. You need a calculator. They're right behind Samara and Khadijah. Yeah. 0.86 molar. That's it. That one's an easy one because I gave you moles and I gave you liters. But if you know how to set it up, it's just division. And you'll see there are 2 sig figs here, so I recorded 2 sig figs. On a scale of 1 to 10, does this make sense so far? 10 meaning I'm awesome. 10. We can divide. All right, thank you. Nurses have to routinely use saline solution to keep their patients' fluids in check. If nurses don't check the concentration of the saline solution, they could potentially cause their patient's cells to burst or shrivel up. Do you remember hypotonic and hypertonic from biology? Okay, this is why that's important. All right. Meaning their patients would die and then they would probably lose their job. All right. A saline solution contains 0.9 grams of sodium chloride. What is sodium chloride in our solution? Small u, good, per 100 milliliters of solution. What is the molarity? So again, what are we looking for? Whatever what? Which is moles over, right, liters of solution. Moles of sodium chloride over liters of solution. Do we have moles of sodium chloride?
No, we have.
So what do we want to do with that? Right, and I'm waiting on you to tell me how to do that. 1 mole of NaCl over, I see us looking at these wonderful things. Maybe there's one in front of you. That'll probably be easier to see. Oh, you're like, duh, let's look at the periodic table and get those masses. The more active participants we have, the faster we get done so you can start your work. What is it? Hold on, 58.45 is our grams. That's the molar mass of sodium chloride. And then tell me what you got for your moles. I'm going to expand that just a little bit. 397. Now, only because this is not my final answer. This is just moles of sodium chloride, right? By 0.1, because it has to be in liters of solution, so it's given to us as milliliters. What's that in liters? 0.100 liters. Okay, so I'm going to take this mole divided by 0.100 liters, and then you guys tell me what that molarity is. Got me? Oh, you don't have your calculator out. 1.5. And actually, I'm going to go back and look at sig figs. So we see 2 sig figs there, so I'm just going to say 1.5 molar sodium chloride. That is what the saline solution, if you've ever had to go to the hospital for anything or you've been there, you've seen the big bags of saline, that's the molarity. And nurses have to understand chemistry so they can understand if they need to appropriate it. Like if a person has a high salt content in their blood, saline is just salt. They can dilute that if they need to, or they can increase the concentration if they need to. So nurses are chemists. Thank a nurse one day. Okay, next. I know, you want to know what I do during my free time, right? Yeah.
So I'm just going to say that I got the 0.01.
Did you multiply?
For the number of moles. And when I divided 0.9 by, yeah, 0.44.
I got 0.01539.
Oh, okay.
I got what?
Oh, okay. You were, I don't think you were. Never mind.
Oh, my bad. Oh, I didn't. Yeah. This decimal goes here. My bad. I sometimes say the right thing and I write the wrong thing. So this would be 0.1, right?
So now like that.
0.15?
Yeah.
Thank you. I'm looking on my calculator. I'm like, yeah, I agree with you, Zach. That's great. But I didn't write it right. Okay. In my free time, I love making solution for chemistry labs. I'm making a 0.24 molar. What's the name of that?
Sodium
Sulfate. How many moles do I need to measure out 1.5 liters of solution? That's our first question, is what? Moles. Okay, so my first question is moles of sodium sulfate.
24. Yeah.
Okay, and then my second question is grams. So tell me what Ooh, I don't like proportions if we can do it a stoichiometric way. What is molarity again? What are the units for molarity? Moles per liter. And what information do I have for volume? Liter. So you just told me moles per liter, and I have liters. What do you think I should do with these two things? Multiply them. And then what happens to liters? They cancel, and then what do you get? Moles. Okay, write this down for yourself. Anytime I give you molarity and volume, I did this in stoichiometry, you probably don't remember, but molarity times volume gives you moles. And the reason why is because molarity is moles per liter. As long as your volume is in liters, liters and liters will cancel, and then it will give you moles. So this is another go-to, like if you ever have to find moles, that's how you find it very easily. And this is the proof of why. Okay, so let's actually plug the numbers in now. So 0.24 moles per liter times, thank you, 1.5 liters. What is that, guys? Say it again. 0.36 moles of sodium sulfate. All right, so that's question one. What's question two?
How many grams?
How would you go to grams?
1 mole of Na2O6 or grams.
Whatever that mass is, right? What is that? Yeah.
What's the grams of sulfur?
Sulfur is 32.06. Oxygen is 16. 142 point what? 005. Okay, sorry. If we had moles here, I was just going with you guys were saying. We're going to convert to grams, so we have to have moles in the bottom to cancel. That's 142.05. 142.005 grams of sodium sulfate. Multiply the moles by the grams for me. Tell me what you guys get for grams. I'm thinking like 40, 51 point. Okay, 1218 grams, and round that to sig figs. 51, because it's only 2 sig figs. Okay, how are we feeling about manipulating data, pushing it together? Okay, on the worksheet I gave you yesterday, look under the solubility curves. It says concentration lecture practice problems. You guys are going to do 1 through 6 right now, okay? And I'm going to probably cut you off by the time you get to 3, because once you get to 3, I'm sure you're going to do the other ones really by yourself. There is one, actually, you know what? I'm going to X 2 of them. Look at them and tell me what you notice. You recognize any of them?
We did number 2.
We did number 2. And we did number 3. Okay, so yay. We've done 2 and 3. So you guys are doing 1 through 6, as many as you can right now. And I want to talk to you about molality. It's just one different unit, and I think once you get how to do the molarity problems, the molality ones are pretty easy.
So we do 1, 4, 5, 6.
1, 4, 5, 6 right now. Yep. You have 4 problems to do right now. Show your work. Show your units. Show your setup, whatever you're going to do. It just goes on to the next page. If you need a calculator, they're right back here. So I'm going to set a timer for about 10 minutes right now to see where we are there. Yes, that to your birthday?
Yes, I did. Thank you. I wasn't sure if you were talking to me at first.
go ahead and write down. Well, actually, look at molality first. So this is continuation of notes. Look at molality, and what are two differences you see?
Number of moles, solutes, over 1 kilogram.
So tell me what's different.
There's not.
Okay, first of all, you're like, hey, we got kilograms here, people. Kilograms, not liters. And what else is different? It's per solvent instead of solution. And then there's one more difference, the way it's written. See at the top? Lowercase m versus capital M. So you see how easily like these could get confused if you weren't really paying attention? I want you to make sure you highlight the differences between these so you understand they are different. Molality is just another way to express concentration. You know, we can express concentration as grams per liters, moles per liters, moles of solute per kilograms of solvent, concentrated, dilute. We can express it as percents. We can express concentration in many ways because it just means stuff per solution. And so this is just another way to do it right here. Little m is equal to this. So instead of saying a 2 molar solution, it's 2 molal solution. I know it sounds like I made it up. I did. Molal. Sounds like a jungle cat. She's a molal in the distance, jumping on the molar. On the mole. Okay. So let's talk. Ooh. I also watched this really scary. What was it? Does anybody watch Sleepy Hollow? The one last night was real scary. I'm like 3 episodes behind. I have nightmares. I'm a wuss. Like these monsters, they're killing me. Okay. So yeah, Hulu. Get on Hulu. Okay, what is the molality? So sorry, back with me. What is molality? Units? Moles of what in this case? Who is a solute? Potassium nitrate. Okay, so moles of potassium nitrate over kilograms of agua. Yes, okay, so that's what we're looking for. Okay, so what's the molality of a solution that contains 55.4 grams of potassium nitrate and 300 grams of water? What's the problem with both of these right now? They're not in the right units, right? So get this one to correct units for me first. 55.4 grams KNO3. What do I do? Okay, what are you calculating? It's molar mass, so 39.1 plus 14 plus 3 times 16. So 1 mole of potassium nitrate is, what did you guys get? 101.1 grams, okay? And what is that? For like 0.5-ish. 0.54797 moles. Okay? So there's our moles of KNO3. Now what do I got to do? Right, divided by 0.3. Right, because 300 grams is, bounce decimal back 3 spaces, is 0.300 kilograms. So divide this by 0.3000 kilograms. What do you get? 1.826. I'm going to round to 1.83 molal because there's 3 sig figs in the top of here. So 1.83 molal of potassium nitrate. To be super descriptive. There we go. Okay, do I need to do another one of these? Okay, I want to give you one warning, and just make sure you're really writing your units down, but also, you know how we did in molarity, in terms of molarity, we're like, oh, molarity times volume gives me moles. Can you adapt that for molality? What would you be doing? Molality times kilograms gives you moles. Simply because the units are different, so it's per kilogram. So this is how you'll get to moles whenever you need to. So highlight those, and then that means now you can do 10 through 13. Okay, so you are not doing 1 through 16 today. 'Cause I'm not going to teach the last day. We have about 10 minutes left, so I want you to make sure you do 1 through 6, and then 10 through 13. Yeah, we're going to go back to 7-8 tomorrow. Can what? We just did 10, thank you. So we just did 10. I tried to do some of them so you didn't have so many to do by yourself. So you're doing technically 11 through 13.
Can you go back to the
Yep, I sure will. Alright, so you guys are doing 11 through 13. Oh, I have a joke. Oh, that hurts. Oh, shut up. It's all in the name of science. Take your $5 and clear out. It's a 5 molar solution. Okay. And here are the answers for you right here.
Oh, is that right? I got that right.
So I'm thinking you can get this done today, so you'll have nothing from class to do. Lord, this could be great. Yeah.
Can you show me just one? Because I think 4 and 5.
I may have been talking about like what
Because I did these two, and I was like, it's because I did this, yes. Which is like, why did you do those two? But that makes sense. Cool.
I see you.